Hey guys, welcome to Physical Sciences again. We'll explore the topic of work, power and energy once more. Now this is part 3 out of 4, which will focus on the concept of work. So in this video we're going to explain what a conservative and a non-conservative force is, as well as the work done by a force, be it positive work and negative work. And then lastly we'll explore the concept of net work done on an object. So let us proceed. So now we have what is called a conservative force. According to the provided definition, it says is a force for which the work done in moving an object between 2 points is independent of the part taken, right? So this one is independent of the part taken. So what this means is that no matter where the object is moving, the direction of that force never changes. Let's take, for example, the horizontal slope, an object of mass m, which is being pulled to the right by a certain constant force F. Now, if we were to draw the free body diagram of this force, due to contact on the surface, we have the normal force, we have the force applied, we have the weight, assuming that this is a rough surface, then we have the frictional force, which is towards the opposite direction as the motion. Now again, let us say we have the very same object with a constant force, but now it is being pulled up an inclined plane by the very same force F, and the mass of the object is m, assuming that this moves upslope. Now the free body diagram of this one, we have a certain force F. The normal force, remember, is always perpendicular to the surface, so in this case it's towards that direction. And then we have the weight, we have the friction, which is downslope. Now if you look at this, firstly, for the horizontal surface, the weight is strictly downwards. For the inclined slope or the inclined surface, the weight is still downwards. So weight is one of the examples of a conservative force, for which is what? Then the work done in moving an object between 2 points is independent of the part taken. So the work done in moving an object between a certain 2 points does not depend on the part taken by the object. Weight will always be strictly downwards, okay? Whereas the applied force and the frictional force can change with time. So we can take the definition of a conservative force to define what a non-conservative force is. It's just the opposite, right? So now the net work done in moving an object between 2 points is now dependent on the direction taken by the object. So this one is dependent on the direction taken by an object. As you can see, frictional force changes with time. If we take another slope again, say now it is being pulled to the left by a certain force F, and if this is a rough surface, you can see that in this case friction will simply be to the right if this object is given that is moving to the left. So a conservative force doesn't change direction at all with time. It's always towards the same direction, just like weight. A non-conservative force is the one which is dependent on the direction taken by the object. So the work done is dependent in what? In the direction taken by the object, or the part taken by the object. So now let us move on. So now we have the concept of work. Fortunately for you, work is defined by the formula. Work is equals to a constant force, delta x, multiplied by cosine of theta. So that's how you start the definition. Define work. Work is equals to F delta x cos theta, whereby F is the magnitude of the force, delta x is the magnitude of the displacement, and theta is the angle between the force and the displacement. So that's how you define work. Firstly, it's the formula, then you explain those individual quantities. Remember that force is measured in newtons, change in displacement or change in x is measured in meters, and that angle theta there, which is measured in degrees, right? Yes, we can proceed. I want us to base our focus on that theta variable there, which is said to be the angle between the force and the displacement, right? So now say we are given an object like this, and then a constant force F that is being applied to the object as it moves between 2 points, a certain X. Now, if we're given that this object is moving to the right, there are 3 options for our theta values. We have theta which is equals to 0 degrees, we have theta which is equals to 180 degrees, we have theta which is equals to 90 degrees. Now let us go ahead and draw a free body diagram for this, provided that this is a rough surface. We have that it's the applied force there, it's the normal force there, it's the frictional force, and then lastly it's the weight of the object, which is Fg, right? So now the block is moving to the right, same direction as the force. So now the angle between the direction of displacement and the force itself is nothing but what? But 0 degrees. Hence, if we calculate the work done by the force, in this case, the work done by the force, which is calculated by F delta X cos theta, whereby F is the force, delta X is the change in displacement, and theta is the angle between the direction of displacement and the force itself, right? As you can see, they are parallel to each other and they are moving towards the same direction. So now we have that this is F, the delta X. Remember, we don't know the force, so we'll assume that it's a certain force F. Now cosine of what? We said the angle there is going to be 0, right? So we have cos 0. But remember that cos 0 is nothing but positive 1. So we now have the work done by the force. Work done by the frictional force. Now if you look at these two, the force and the frictional force, the object is moving to the right, it's being displaced to the right, but the frictional force is moving to the left now. If you think of this, there's 180 degrees. Of course, the frictional force and the direction of displacement are parallel to each other. I agree to that. But now there's a difference in direction. One is moving to the right, one is moving to the left. So we can measure the angle between the direction of displacement and the frictional force to be what? To be 180 degrees. So we have that now. Work done by the frictional force is equals to the frictional force, delta X, cosine of theta. Now what's the frictional force? Okay, it's given that it's a certain frictional force F, delta X. We are going to use cosine of what? Cosine of 180 degrees, because when we measure the angle between the displacement, the direction of displacement, and the direction of the frictional force, it gives us a 180 degrees since they are opposite directions. Think of it as if you are placing a protractor now. So think of it as if you are placing a protractor. This is the direction of displacement. This is the direction of the frictional force. So if you look at this, if we place a protractor directly between those two, you can see that the direction of displacement is our 0 degrees all the way to the direction of the frictional force gives us a what? 180 degrees. So from here, we have that this is F delta X cos 180. But cos 180 is what? It's negative 1. So we have delta X into negative 1. Okay? So now we have the work done by that. Let us calculate the work done by the normal force. The work done by the normal force. Now, if you look at the direction of the displacement, remember that displacement is towards the right, but the normal force is simply upwards. So there's a 90-degree angle between the direction of the normal force and the direction of the displacement. So work done by the normal force is simply F delta X cos what? Cos 90, right? But cos 90 is nothing but 0. So you have F delta X to be multiplied by a 0, which is simply 0. So the normal force is doing no work. And we'll explain that shortly why there's no work done by the normal force. Now moving forward, we have work done by the weight. You can see the weight is also, the direction of the weight is downwards, whereas the direction of the displacement is towards the right. So what happens there? There's a 90-degree separation again, meaning the work done by the weight is 0 also, right? And another thing to remember that I forgot to mention is the fact that work is measured in joules, because we are simply dealing with energy here. So now I want us to use the previous information to work something out. We have positive work, we have negative work, and lastly we have no work done. So it's positive work being done to the system, negative work being done on the system, and lastly we have no work being done on the system. So now amongst those forces that act on the object, we will classify which ones do positive work, which ones do negative work, and which ones do no work. And again, let us focus on the free body diagram that we had previously, in which we had the normal force, we had the applied force, we had the weight, and then we had the frictional force. Provided that the object is moving to the right now, the change in displacement is towards the right. So now which force is going to do a positive work? It's the applied force. Why? Because it is given that this object right here follows the same direction as the applied force. It's like the applied force is adding energy into the system such that it gives it the required energy to move in whatever direction that is the same as the what? As the applied force, right? So the applied force and the displacement are in the same direction. If the force and the displacement are in the same direction, then that force is doing positive work, okay? So delta X and the force itself in the same direction or towards the same direction, then that's when an object does positive work. And then what angle do we use there? We use a theta which is equals to 0 degrees. And why is that? This is derived from the cosine function. The cosine function is like this, whereby you have a 0 degrees there, somewhere here you have a 90 degrees, and then there you have 180 degrees here, which corresponds to a what? To a -1. So it's 180 and -1. If it's doing positive work, you are looking for the part which is going to give you a positive answer whenever you substitute into the formula. Work is equals to F delta X cosine of theta. So when you substitute cos 0, you get a +1. Hence, this whole thing is going to become a positive value, right? Let us look at negative work. Negative work, the direction of displacement now. The displacement, if the displacement is towards that side and maybe the force is towards that side. Now, it's like this force is subtracting from the system. It's working against the system itself. If we focus on the given free body diagram there, you can see that the displacement is towards the right, right? We have a displacement that is towards the right, but the frictional force is towards the left. So it's like it's working against the system. It's slowing the system down, right? You know, frictional force is always slowing objects down. So the frictional force is the one which is doing negative work. And then what are we expecting? We are expecting a negative value there. So if delta X and a certain force, which is F, are in opposite directions now, then what happens? Then that object or that force is doing negative work. It means it's acting against the system. It's taking from the system, right? So what angle are we going to use there? We're going to use theta is equal to 180 degrees, because at cos 180 degrees we have a -1. Hence the formula now, work is equals to F delta X cosine what? Cosine 180 degrees. But remember that 180 degrees, cos 180 degrees is what? Is nothing but a -1. So you have that. Now no work. For no work, if now delta X and a certain force F are perpendicular to each other. So if they are perpendicular to each other, then no work is being done by that force, right? Just like the weight and the normal force there, those ones are doing no work. Reason being, think of it like this. The block is sliding on a horizontal surface. There is no movement up or down. The block is simply either sliding to the right or to the left, but it's not moving up or down. Hence, there's no work being done by those two forces. But another way to look at it is what? You have the displacement and then you have the normal force. There's a 90 degrees in between these two. So work done now by the normal force is equals to F delta X cos 90 degrees, because that's the direction between, that's the angle between the displacement and the normal force. Cos 90 is 0, then this gives you 0. And so is the weight. Now let us summarize that quickly. If delta X and the force, yes, if the change in displacement and the force are in the same direction, we have positive work being done. Now, if delta X or the change in displacement and the force are in opposite directions, then you have negative work being done. And then if you have the change in displacement and the force being perpendicular to each other, then that force simply does no work on the system. Okay? Let us say maybe we have an object, then we have a certain force that is applied at an angle now, an angle of 30 degrees. Let's say the force is equals to 100 newtons. This is resting on a horizontal surface. It's a block of 10 kilograms. Say that this is a rough surface. First things first, we're going to have to work with the free body diagram, then calculate the work done. So we have that force right there, which is 100 newtons at a certain angle of 30 degrees. We have the weight, we have the normal force, and we have the frictional force. Let us just assume that the frictional force in this case is just equals to 5 newtons to the left. So we have 5 newtons for the frictional force. So now we are going to calculate the work done by the force, applied force, the work done by the frictional force, the work done by the normal force, and the work done by the weight. Now for the work done by the force, the applied force, remember it's F delta X cosine of theta, provided that this block is sliding 2.5 meters towards the right. Okay, so what's the force there? The applied force is 100 newtons. What's the change in displacement? The change in displacement is 2.5 meters. And then cosine of, sometimes it's easier to use the angle. You can see that the displacement is towards that direction and the force is 30 degrees with respect to the horizontal. So the angle between the displacement and that force there is 30 degrees. So you can even say it's cos 30 there. That's a 216.51 joules. Okay, this will always work out, it's fine, but I don't encourage you to use the angle right there for the angle with respect to the axis for the force. Rather, resolve the force back to its components, right, such that you have the x component and the y component of that force. So what happens, your free body diagram now becomes what? Remember that this force has two components. You have the x component and you have the y component. So now it's going to be fx, and then in that direction you have your fy, and you have the normal force. Now there's two forces in the y direction, and then you have your frictional force and you have your weight there. But now remember how you calculate those ones. This will give you, this is fy, this is fx. What's the angle? It's 30 degrees. What's this? This is the hypotenuse, which is 100 newtons. So now you can see that your fy is the opposite. So you use sine of that. Sine 30 is equals to opposite divided by hypotenuse, which is 100. So your fy is equals to 100 sine 30. Now the other one, for the fx, obviously it's just going to be fx is equals to the cosine of that angle, 100 cosine of 30, right? Yes. So now if you look at this, remember that on this free body diagram, the direction of displacement is to the right. So we are going to calculate the work done by those individual components of the force. So we have work done by fx. work done by Fx, we have what? 100 cosine of 30, that's the force itself, that's Fx, multiplied by delta x, which is 2,5. Remember now, the object is moving to the right, Fx is also moving to the right. What's our theta there? Our theta is simply equals to 0 degrees. It's doing positive work, so we have cos 0, which is just 1. So this will give us 216,51. So this will give us 216,51 joules. Now let us look at the force done by the y component. Now if you look at the y component, the direction of displacement is to the right. The y component of the force is upwards. So there's a 90 degrees separation between the direction of the displacement and the force itself. So we have what? We have 100 sine 30. Remember, this is Fy multiplied by the displacement, which is 2,5 cos what? It's cos 90 because now it's perpendicular to each other. But remember, cos 90 is 0. So this is 0 joules. Hence, the y component of the force is doing no work. Which one is doing work? It's only the x component of that force. So now it's much more easier than to take the angle which was measured with respect to the axis for the force. Okay, let us proceed. Calculate the work done by the frictional force. Remember, we are given frictional force to be 5 newtons. 5 newtons in what direction? To the left. So what angle is that? Remember, the displacement is to the right, so there's a 180 degree separation between the two, hence theta is equals to 180 degrees. So work done by the frictional force is equals to what? Is equals to frictional force delta x multiplied by cosine of what? Of 180 degrees. And then this is 5 multiplied by 2,5, and then this is cos 180, which is negative 1. So it's just 5 times 2.5, 0.5. It's gonna come out as negative. It's minus 12.5 joules. But remember that energy is a scale, so it's 12,5 joules, which is being taken from the system. So friction is actually subtracting from the system, right? Yes. And the rest of the other forces are doing no work. You can see that the direction of displacement is to the right, and the normal force is perpendicular to the direction of displacement, as well as the weight is perpendicular to the direction of displacement. Hence you have a 90 degrees there, which will give you a 0. Let's proceed. We are given this object right here. It says that a worker pulls a crate of mass 30 kg from rest along a horizontal floor by applying a constant force of magnitude 50 newtons at an angle of 30 degrees. And again, remember what I said. As soon as an angle is measured with respect to that, what do you have to do? You have to resolve it back to its components so that you can use theta is equals to 0 degrees, theta is equals to 180 degrees, or theta is equals to 90 degrees, okay, for the work done. And a frictional force of magnitude 20 newtons acts on a crate while it's moving along the floor. Define the term work. Remember, we said work is going to be defined by the formula work is equals to F delta x cosine of theta. And then you're going to explain these individual quantities, whereby F is the magnitude of the force, delta x is the change in displacement, and lastly theta is the angle between the displacement and the force applied, right? Yes. Draw a label free body diagram showing all the forces that act on the block. So remember this. Yeah, the block is in contact with the surface, hence it has a normal force. The force is applied at an angle of 15 newtons there, but the angle is 30 degrees, right? And then we have a weight, or Fg, and then we have the frictional force. When it comes to the free body diagram, if it's 4 marks here, then they're expecting you to account for 4 forces. So it's 1, it's 2, 3, 4, okay? Yes, this free body diagram is correct, but then the problem is that force is measured with respect, it is measured at a certain angle with respect to the x-axis, right? Okay, fine. It can work, but I'd prefer you to draw the free body diagram in this way now. Resolve it back to its components. Remember, it has a certain x component and it has a y component. It's fine if you draw it like this, but in component form, you have it as Fy, you have the normal force there, and then you have the weight, and then you have the x component of the force. Lastly, you have the frictional force. Now the marking, this one and this one are going to be marked together as one. And then the next question says, calculate the magnitude of the horizontal component of the applied force. Remember, the applied force is in that direction. Then it has an x component, it has a y component at what? There's a 30 degrees angle, but this hypotenuse here is 50 newtons. So they are looking for the horizontal component, they are looking for fx. So we are going to use trig ratios. This is the adjacent side. So the cosine of that angle, cosine of 30, given that this is 2.3.1, cosine of 30 is equal to the adjacent, which is fx, divided by the hypotenuse, which is 50 newtons. Multiply both sides, you get that fx is equal to 50 multiplied by the cosine of 30, 43.30. So this is 43.30, but remember this is a force, so it's in newtons and it's to the right. And then they say calculate the work done by the horizontal component of the applied force. So now work done by fx is simply equals to, this is 2.3.2, is equals to fx itself multiplied by delta x and cosine of what now? Remember, the object is sliding from point O to point P, so delta x is in that direction, meaning that force fx is doing positive work. And if a force is doing positive work, what's our theta? Our theta is equals to 0 degrees. So we have that this is, okay, I don't want to use the answer that's been rounded off. I'd rather use f cos 30. What's delta x? 6 meters is given there. And then what's, oh, remember this is cos theta. And we have that this is cos 0, which is just positive 1, which gives us 259.81. But remember that even if we had used that force there, the work done by the force is equal to the force itself changing x, cosine of what? It's going to be cosine of 30 now, because we are saying that displacement, it's that 0 line there, and where's the force? The force is in that direction. So between the change in displacement and the force of 50 newtons, there's a 30-degree angle separation there. So this becomes 50. What's our delta x? It's 6. And what's our cosine of theta? Sorry, our cosine, our theta now becomes 30 degrees. And then this gives us 259.81 joules. And what's that? That's exactly that, same thing. So when you take the horizontal component of the force, it gives you the very same work done by the force, because the y component of that force is not doing any work. Displacement is in that direction, which is perpendicular to the direction of the y component. Now they say calculate the work done due to friction. Frictional force acting on the box. Remember, the friction was given as 20 newtons and it's to the left. So we have work done by friction. But remember, what kind of work is being done by friction? Friction is doing negative work. And whenever a force is doing negative work, what are we expecting? We're expecting theta is equal to 180 degrees. So we have frictional force delta x cosine of 180 degrees. So it's 20 newtons into 6 meters cosine of 180, which is just negative 1. Yeah, so this gives you a negative 120 joules. But energy is a scalar, you can't have a negative. So it becomes what? 120 joules taken from the system. Okay. Yes. So now we can proceed to do one last thing there. Let me erase this. There is the concept of net work done, or work net. The net work done on an object, which is work net. So this is just a summation now. It's just a summation of what? Of all the work. But in this case, you can already see that if you sum up all the works being done, the individual work being done on the object, you have that this is doing no work, so it's cancelled out. you have that the Fy is doing no work. It's also cancelled out. The normal force is doing no work, and you know why? Because the delta x, or the displacement, is towards the right, and those forces are perpendicular to the direction of displacement. The only two forces that are doing work, it's actually the x component of the force and the frictional force. So now work net in that system, the work net is just going to be the work done by Fx plus the work force. Yes, remember we had this as what? As 259.81 joules minus, remember this came out as minus 120 joules, is subtracting from the system the 139.81 joules, and then you can see that this is what? This is positive work now, because we are getting a positive value, hence the block is moving to the right. But there's another way to obtain this value again, right? Remember that the two forces that are doing work there, it's the x component, which is 50 cos 30, and the frictional force Fk, which is 20 newtons. This is to the right and this is to the left. You can do a force summation and say the sum of forces in the x direction. You know that this object is moving to the right only, so that's why we are only doing force summation in the x, or in the x direction. Let's take to the right as positive. This will give us what? It gives us that we have 50 cos 30 plus the friction is to the left, so it's minus 20 in this case. And then this gives us 23.30. So that's the resultant force, in fact. That's the resultant force in that object. And you can see that this is positive. So since this answer is positive, what are we expecting it to do? It's doing positive work. And if we substitute in the formula for work, we are expecting theta to be 0 degrees. So we can therefore say work done by that resultant force is equals to F delta x cosine of what? Of 0. What's the force itself? It's 23.30 delta x, which is 6 as given, cos 0. So what's this? Times 6, which is 139.81 joules. And what's that? 139.81? It's the one we found whenever we do the summation of the individual work. So you can either take the long route of calculating the work done by that and the work done by that, and you sum them up and substitute with the respective signs, or you can just do a force summation and find the resultant force, and that's it. If you get a negative answer, you know it's doing negative work, so it has to be cos 1/8. Now, to sum up everything we spoke about a conservative force. We said the work done to move an object between 2 points is independent of the path taken. We said whether an object is moving up or down, this one doesn't change direction, and we said it's the weight, right? The weight of an object is an example of a conservative force. And then we had a non-conservative force, whereby we said the work done to move an object between 2 points now is dependent on the path taken. And then the example was frictional force, which changes from time depending on the direction taken by the object. We later on had the work done, which is F delta x cos theta, in which we said F is the magnitude of the force, delta x is the change in displacement, and theta is the angle measured between the direction of the displacement and the force itself. We later on classified this as positive work. We said for positive work, you are going to use theta is equals to 0 degrees. And then we said for positive work, you must know that delta x and the force itself are moving towards the same direction. Then we had negative work. For negative work, we said theta is equals to 180 degrees now, whereby we said the change in displacement and the force now are in opposite direction but are still parallel to each other. Then we had one which does no work. We had that theta is equals to 90 degrees. Then we said the force now, the force is perpendicular to the direction of displacement. You have a theta which is 90 degrees. And remember that cos 0 will give you a positive 1. Cos 180 will just give you a negative 1. And then cos 90 will give you a 0. Hence, positive work, you have positive 1. Negative work, negative 1. No work, you have a 0 there. It is all derived from the cosine function, which goes like that. Whereby this is 0 degrees, it's at positive 1. At 90 degrees, it's at 0. At 180 degrees, it's at negative 1. You see where all these things come from. Yes. So now we will use this. And we said, lastly, we have the net work done on an object. The net work done is equal to the work done by force number 1 plus the work done by force number 2 plus the work done by force number 3 plus, depending on how many forces you have, right? But you must take into consideration the sign. If you get negative work, you're going to substitute this as negative there. And lastly, we said if you don't want to use this, you can use force summation first. Sum of fx. Let's say you take the original part taken by the object as positive, and then find out what's the resultant force there.